Hi, and welcome to the next training video in the Living Landscapes project. In this session, we're going to look at how we visualise Lidar data and how to interpret the images it produces. You'll see how different techniques like hill shading and simple local relief modelling can help us bring out subtle features in the landscape that aren't visible in the raw data or aerial photos. We'll explore how these visualizations work, what they're good for, and how to start recognizing archaeological features like banks and ditches. By the end of this video, you'll have a stronger understanding of how to read LiDAR imagery and spot patterns that might point to past human activity. So before we go any further, it's really important to understand what we mean by earthworks. These are human-made changes to the landscape. They are features created by digging, piling, or shaping the ground. Many of them were built hundreds or even thousands of years ago, and although some may no longer be visible to the naked eye, they've left behind subtle traces in the terrain. And LiDAR helps us detect these traces by showing tiny differences in elevation. So the first one we're going to talk about is a bank. So a bank is a raised strip of ground, often formed by piling up soil or stone. Banks were commonly used to mark boundaries, enclose fields, or form part of defensive structures. In LiDAR visualizations, banks appear as slight ridges or raised lines across the surface. And we'll explore these types of features in more detail in another session. But before we dive into the LiDAR visualizations, it's helpful to know what kinds of things we're actually looking for, so you can start to recognize them in the landscape and understand why they matter. A ditch, on the other hand, is a long, narrow depression cut into the ground. Ditches might have been used for drainage, as part of a boundary, or for defense. In LiDAR visualizations, they show up as sunken lines or channels, often running alongside banks. A mound is a rounded pile of earth or stones, sometimes created for burials, rituals, or territorial markers. These can be prehistoric barrows or modern features. And in LiDAR visualizations, they appear as raised circular shapes or bumps in the terrain. You might also come across features like pits, which are small depressions dug into the ground. These could have been used for storage, rubbish disposal, or extracting materials. In LiDAR, pits appear as small dips or dark spots. Larger excavations like quarries were used to extract stone or other resources. These tend to look like big sunken areas with steep sides and irregular shapes. So all of these features, the banks, ditches, mounds and pits, are part of the story left behind in the landscape, and LiDAR helps us read that story by making the invisible visible. So just to recap in our last session, after we filtered our point clouds to show only the last pulse return, we then interpolate those points to create a digital terrain model. This gives us a representation of the bare ground with the trees and buildings removed. But as you can see from our example here, the raw DTM doesn't always reveal much on its own. And that's why we need to manipulate the data using visualization techniques to bring out subtle features in the landscape, like our banks and ditches. Don't worry, this processing has already been done for you, but it's useful to understand how it works so you can better interpret what you're looking at and recognize the kinds of features we're trying to uncover. So what we're looking at here is a digital terrain model of a part of Exmoor. This is unmanipulated data, meaning that no visualization techniques have been applied yet. In this image, every pixel represents elevation, and the color indicates height. The darker areas black are lower in elevation. These are the valleys, where you'll often find springs and rivers. The lighter areas, the white, are higher up. These represent the moorland ridges and uplands. So to help orientate you, I'm now showing a map of the area we've been looking at. This gives some geographic context to the DTM image. The darker area you saw earlier corresponds to the River Ex, which runs through the valley. The lighter area, higher in elevation, is part of the Chains Ridge, a stretch of upland in Exmoor. By linking the elevation data to real-world locations, we can start to interpret the landscape more meaningfully and understand how natural features like rivers and ridges shape the terrain, potentially influence where archaeological features are found. Although this gives us a basic sense of the terrain, it's still difficult to pick out finer details of archaeological features. That's why we use visualization techniques to enhance the data and make subtle features easier to interpret. To create the visualizations you'll be seeing, I've used a piece of software called the Relief Visualization Toolbox, and it was developed by a team of brilliant statisticians, specifically to help interpret elevation data like our digital terrain model. These manipulated images are what I refer to as visualizations throughout the rest of this video. So let's take a look at our first visualization, hill shading. This is one that many people are familiar with if they've worked with Lidar before. It helps us see the shape of the land by adding shadows and highlights, almost like shining a light across the terrain. To help us understand what we're looking at, I've included an image of our study area. So this is an aerial photograph of Loch on Exmoor. By showing this photo first, we can get a sense of the landscape and where we are focusing. Now, this is our digital terrain model of Loch Barrow, the exact same area we just saw on the photo. The Relief Visualization Toolbox creates an analytical hillshade by pretending there's a sun, usually placed in the northwest. It then casts light from that imaginary sun across our digital terrain model. As the light hits the terrain, it creates shadows and highlights based on the shape of the land. And this is what our analytical hillshade looks like. You can start to see how the landforms stand out more clearly here. Ridges catch the light and appear bright, while valley slopes that are facing away from the light appear dark. It gives us a much better sense of the landscape and the raw DTM alone. In this visualization, we can begin to start picking out some archaeological features we talked about earlier. You might notice a few rounded raised piles of earth. These are likely mounds, possible burial or marker features or something later. There's also a raised strip of ground, which could be a bank. And you'll see lots of long, narrow depressions. These are our ditches cutting through the terrain and often running alongside banks. We can also see small pits, which in this area are likely to be World War II shell craters. In Lidar, they appear as small circular depressions, often clustered together. Now let's look at another visualization called Simple Local Relief Model. This one is really helpful for spotting small features in the landscape that might be hidden in other views. It works by taking away the big hills and valleys, so the overall shape of the land, and leaves behind just little bumps and dips. That way we can focus on the details. Think of it like smoothing out a crumpled sheet of paper and then looking at what's still sticking up or dipping down. Those small differences are often where we find things like old field boundaries, burial mounds, banks and ditches. In places like Exmoor, where the land gently rolls, this visualisation helps us see the subtle traces of past human activity that are easy to miss. This is different from analytical hillshade, which uses light and shadow to show the terrain as if it's being lit by the sun. Our analytical hillshade gives us a more natural 3D look to the landscape, but it can sometimes hide features if they're not aligned with the light source. The simple local relief model, on the other hand, removes that lighting effect and focuses purely on the shape of the ground. In this visualization, the white pixels represent upstanding features. So these are the banks and mounds that rise above the surrounding ground. The black pixels, on the other hand, show depressions cut into the ground, and these are our ditches and pits. Now let's take a look at another visualization, sky view factor. This visualization is especially good at showing how open the sky is from each point on the ground. It works by calculating how much of the sky is visible from each pixel in the digital terrain model. So if a point is in a dip or surrounded by raised features, it will have less sky visible and appear darker. If it's on a ridge or open ground, it will have more sky visible and appear lighter. This makes sky view factor really useful for spotting earthworks like banks, which block the sky and show up as dark edges. Ditches and pits, which are sunken and also appear dark, and mounds, which stand out because they appear lighter because they're more exposed to the sky. So when reading a sky view factor, look for dark lines and patches. These are likely our ditches and pits at the edge or the edges of banks. And look for lighter spots, and these may be mounds or raised areas. Now our final visualization is visualization for archaeological topography, or what I'll be calling VAT. This one is designed specifically for archaeological work. It helps us spot subtle features in the landscape that might be missed in other visualizations. What makes VAT so powerful is that it combines several different visualizations into one image, giving us a much richer view of the terrain. So VAT blends the analytical hillshade, which adds depth using light and shadow, the sky view factor, which shows how open the sky is from each point, and other visualizations that we haven't covered in these sessions, such as slope analysis, which sharpens edges and boundaries, positive and negative openness, which highlights banks and ditches, and local dominance, which shows how dominant a point is compared to its surroundings. By layering these together, VAT enhances both raised features, like our banks and mounds, and cut features, like our ditches and pits, making them easier to spot even when they're faint or partially eroded. So how do we read VAT? Well, our bright areas usually mean upstanding features like banks and mounds. Dark areas show depressions like ditches and pits. Sharp contrasts help define boundaries and shapes, especially enclosures. Each of our 4 Lidar visualizations we're using, so the analytical hillshade, simple local relief model, sky view factor, and VAT, has its own strengths and weaknesses. Hillshade gives a familiar 3D look using light and shadow, but it only shows features clearly if they line up with the light source, and it doesn't distinguish well between large and small features. The simple local relief model is great for highlighting small bumps and dips like banks and pits, especially in gentle rolling landscapes. However, it doesn't work well in very steep terrain where dramatic slopes can overwhelm the subtle features we're trying to see. Sky view factor helps us spot how open or enclosed the land is, which makes it useful for finding ditches and raised features, especially in wooded or complex areas. That said, sky view factor can appear pale or low contrast, and small features may be blurred. VAT is the most detailed. It blends several techniques, including hillshade, sky view factor, slope analysis, openness, and local dominance to show both raised and sunken features. It's designed for archaeology and works well in complex landscapes, though it can look quite busy and it takes time to get used to reading it. So each of the visualizations we've looked at are analytical hillshade, simple local relief model, sky view factor, and VAT has its own strengths and limitations. Some are better at showing features than others. You may have already noticed or will begin to notice that certain features stand out more clearly in one visualization than another. There are many other visualizations that can be created using Lidar data, but for this project, we're focusing on these 4, as they're especially useful for interpreting the Exmoor landscape. It's important to remember that these visualizations work best when used together. So by comparing them side by side, we can build a fuller picture of the terrain and spot features that might be missed if we relied on just one. If you're interested in exploring more visualization techniques or diving deeper into how these tools work, we recommend checking out the RVT guidebook, which offers detailed explanations and examples. So just a quick recap. In this session, we learned how LiDAR data is visualized to help us detect subtle archaeological features in the landscape. We explored 4 key visualizations: the analytical hillshade, simple local relief model, sky view factor, and VAT, each with its own strengths and limitations. Some are better at showing raised features like banks and mounds, while others highlight depressions like ditches and pits. By using them together, we get a fuller picture of the terrain and can spot features that might be missed if we relied on just one. These 4 are especially useful for interpreting the Exmoor landscape. Thanks for watching, and I'll see you in the next session.